Hello, everybody, and welcome to another online version of the Cosmic Adventure Astronomy Lecture Series. My name is Dr. Valerie Rapson, and I am the Director and Astronomer at the Dudley Observatory. Today, we're going to be talking about the significance of star clusters. Star clusters are these beautiful collections of stars that you can spot in the nighttime sky, and we're specifically going to do a brief overview of all the different types of star clusters. We're going to talk about why they're important to astronomers, specifically how they tell us where we are located in the Milky Way, and about how old our Milky Way galaxy is. And then we'll finish up with some tips and tricks on how to find some of these star clusters with your own eyes in the evening sky tonight. So sit back, relax, and enjoy learning about star clusters. We'll begin by answering a simple question: what are star clusters? Well, in general, star clusters are just a dense collection of stars that appear in one specific location in the sky, and we believe that they all formed from the same dense cloud of gas and dust. If you take a look in the bottom right-hand corner here, we have an example of a globular star cluster. This grouping of stars is called M22. The M stands for Messier. It's a catalog of objects that are visible in the nighttime sky, and 22 just means it's the 22nd object in that catalog. M22 is a globular star cluster, and we'll talk about the different types of star clusters in a moment. But basically, it's just many, many stars in one spot in the sky, and they're all so densely packed that the stars are bound together by their mutual gravity, meaning that any one star feels the pull of all the other stars, and that helps keep them all located together in the same spot. Now, M22 is a special globular cluster. It was the first globular cluster ever to be observed by a telescope way back in 1665. And it wasn't until almost 100 years later that telescopes improved to a point where we could actually look at this star cluster and tell that it was made of individual stars. Originally, it just looked like a bright yellow fuzzy patch to the astronomer. And as telescopes got bigger and better, we were actually able to resolve individual stars. And nowadays we can take really beautiful pictures like the one you see on the right-hand side here that have many, many individual stars. And we can use this picture and use this information to learn a lot more about the individual stars themselves, as well as the cluster as a whole. I mentioned before that there are different types of star clusters, and we're going to focus on the two main types of clusters today. There are globular star clusters, and there are open star clusters. We'll start with globular clusters, and they are exactly what the name sounds like. They look like globs of stars tossed up into the sky. More scientifically, globular clusters are tightly packed regions that contain about 10,000 or more stars that are usually packed within about 100 light years or less. If you take a look at the two pictures here, you can see that they really do look like globs of stars in the sky. Globular cluster M80 is on the left. So all of the stars you see here in the picture, the white and yellow dots, those are all part of the star cluster. This cluster is about 28,000 light years away from the Earth, away from the solar system, and it's about 95 light years in diameter. So from left to right in the picture, it's approximately 95 light years. We don't really have a good sense of depth in a lot of these pictures. It's hard to tell how far away a foreground and a background star is in a star cluster. Usually our measurements of distance are not that precise to where we can talk about them being, just a handful of light years apart from one another. The error bars are usually too big in our measurements to say that. So we don't really have a good three-dimensional view of these star clusters, so we just quote an approximate visual diameter. So about 95 light years across, that's where those about 10,000 stars are. The image on the right, this is NGC 6397, another globular star cluster. This one is a lot closer to us. It's only 7,800 light years away. And it's a lot smaller in size. It's only about 4 light years wide. So all the stars you see here are packed into a region only 4 light years wide. Now, to really help give you a sense of how tightly packed globular clusters are, we can not only talk about number and size, but we can talk about density. How many stars per light year do we have? Well, most globular clusters have about 100 to 1,000 stars per light year. Now, let's compare that to the solar neighborhood. If we think about our sun, the nearest star to us, Proxima Centauri, is about 4 light years away. So in the solar neighborhood, we have one star every 4 light years. In globular clusters, you can pack as many as 1,000 stars into 1 light year's distance. So these really are regions tightly jam-packed with stars. They're very close to one another in outer space, and they really feel a sense of gravity from one another. In total, astronomers have discovered about 150 globular clusters throughout the Milky Way galaxy. So how do these globular clusters form? Well, we mentioned already that star clusters in general form from clouds of gas and dust. And basically what happens is you have this large nebulous cloud. Gravity begins to collapse small portions of the cloud. And as those portions collapse, they're going to form individual stars. And if the cloud collapses pretty much all at once, making hundreds or thousands of stars all at approximately the same time, then you end up with a star cluster. That's the basic idea. Globular clusters go through a similar process, but they come from a collapse on a much larger scale. Globular clusters actually formed very early on. They actually formed at the same time our entire Milky Way galaxy was forming. So imagine that giant cloud of nebulous gas, except make it so big that it's literally the size of our Milky Way. In our cartoon here, we start with this nebulous cloud of gas that will eventually form our entire galaxy. And the particles, the gas particles, are moving around all over the place, but they have a general bulk motion, in this example, counterclockwise. You can see that there are some arrows here moving counterclockwise. As time goes by, the particles start to get pulled together by gravity, and this nebulous cloud is going to collapse into a disk. As the disk continues to spin, you're going to form lots and lots of stars. You're also going to have a large collection of material in the center. That's what will form the supermassive black hole. And the end point here is going to be our Milky Way galaxy, a galaxy filled with stars and gas and dust that is spread out into this lovely spiral arm structure. Throughout this process, we will end up with star clusters, and globular clusters actually tend to form at the very beginning. So if I add another piece to our cartoon here, as soon as this large nebulous cloud begins to collapse, in the outer regions, you're going to have pieces of the cloud that collapse faster. They are going to form tons and tons of stars in a very small space, and that is going to become your globular cluster. So if you look at the cartoon on the bottom right, you can see that all of the blue has collapsed down, or it's starting to collapse down to form the galaxy. And above and below the plane of the galaxy, you see there are these white dots. Those white dots represent globular clusters. So these clusters of stars actually formed before the entire Milky Way galaxy formed. So what we see then is globular clusters that are generally above and below the flat plane of the galaxy, and they're going to be very old. They're going to be tens of billions of years old. They're going to be at least as old, if not slightly older, than our whole Milky Way galaxy. So globular clusters form at the very beginning stages of actually forming an entire galaxy. So as we mentioned, globular clusters formed at the very beginning of the formation of the Milky Way, and that was about 10 or 12 billion years ago. So what that means is if we look at the globular clusters today, what we're going to see is a collection primarily of smaller, lower mass, older stars. We're not going to see any brand new young stars because so much time has elapsed. All of those young stars have either aged 10 to 12 billion years or they've lived out their entire life, they've evolved, and they've died. So globular clusters primarily contain these smaller, older, lower mass stars. Any high mass stars, which evolve much faster than these lower mass stars, will have lived out their entire lives and they will be completely gone. And we're going to talk about how this is the key for determining the age of star clusters in a little bit. That's how we're going to determine how old these star clusters are by looking at what stars are left in the cluster. But overall, globular clusters only have smaller, older stars in them. And as we said previously, they're primarily found above and below the plane of the galaxy. If you take a look at the cartoon here, we're showing an edge-on view of our Milky Way. You have the central bulge, that is where the supermassive black hole is, and it's a little bit thicker in the middle because you have stars orbiting above and below, as well as around the outside of the supermassive black hole. And then from the side, you can see the spiral arms are very thin, so it looks like a straight line, a thin flat disk here. We in the solar system are about halfway between the center and the edge of the Milky Way, and globular clusters are represented by these white dots above and below the galaxy. So globular clusters tend to be above and below the plane of the Milky Way galaxy. One more cool thing to know about globular clusters is that because there are so many stars so tightly packed together, the gravity between two stars can really disrupt one another, and sometimes it can actually kick out stars. So when we look at a globular cluster, like for example M13 shown on the right, we generally see a very, very bright center, showing us that many of the stars have collapsed down to the center, right? The gravity is stronger at the center of the cluster because a lot of stars have formed there, and their gravity is going to pull more stars in. Well, if a star from the outside starts to fall towards the center of the cluster, those strong gravitational interactions will either pull the star in and it will become part of the center of the cluster, or the gravity will be so strong that the star comes flying in, slingshots around the center of the cluster, and gets kicked all the way back out again. So some of the measurements that astronomers have done with globular clusters show that many of the clusters have a velocity inwards, meaning if I picked any one of these single stars, most of them would be moving gently towards the center. But occasionally you'll have a couple of stars on the outer edge with a complete opposite velocity, flying outward. Those stars have likely fallen towards the center, slingshot around the center, and are on their way back out. They got kicked out of the system. So occasionally you'll see a sporadic star in the sky that's somewhat near a star cluster but kind of headed in the opposite direction, and it's very likely a star that got kicked out of the system. Globular clusters have such strong gravitational pulls that they often disrupt the natural orbits of the stars like that. All right, so globular clusters are pretty cool, but let's move on to talking about open clusters and the similarities and differences between these and the globulars. An open cluster is a star cluster, but it's generally much smaller, more loosely packed, and contains a variety of stars of different sizes and masses. If we take a look at a couple examples here, we have the Pleiades. The Pleiades is a very famous open star cluster. Easy to see with your eyes in the wintertime. It's part of the constellation of Taurus the Bull. It's only about 444 light years away, 35 light years in diameter, and it contains just a few hundred bright stars. So you can see all of these blue stars here. Those are part of the Pleiades open cluster. On the right-hand side, NGC 290. This is an open cluster that's actually part of the Magellanic Clouds. These are satellite galaxies orbiting the Milky Way. And this one sits about 200,000 light years away from the solar system. 65 light years in diameter. And it looks like there's a ton of stars here. It looks very similar to a globular cluster. But most of the stars that are technically part of the cluster are the bright blue and bright red ones that appear in the foreground. Many of the little white dots in the background, those are literally background stars, and they're not technically part of the cluster. They're just in our line of sight when we're looking at this star cluster. So open star clusters, they generally, as we said, contain stars of a whole variety of masses. You can have both low mass and high mass stars, and that's because they tend to have been more recently formed. Open clusters tend to be somewhat younger, so the massive stars haven't died out yet, and there's also just regular low mass stars there as well. And we often see gas and dust still a part of the open clusters. When we looked at globular clusters, we literally just saw stars. When we look at open clusters, we often see some nebulous material around the stars. Not always, but that's often the case. Open clusters generally exist within the plane of the Milky Way galaxy, so they tend to be within the spiral arms. And so far, we've discovered about 1,100 of them throughout the Milky Way galaxy. Let's talk briefly about how we form open clusters. Open clusters form when a giant molecular cloud or a big nebulous cloud of hydrogen gases collapses to form a bunch of young stars. Now, forming a cluster of stars in general, whether it's open or globular, usually takes 10 to 100 million years. Open clusters have formed more recently, usually within the last couple hundred million years or more recently. And if you take a look here at the two pictures, we have NGC 3572 on the left, beehive cluster on the right. You can see, especially on the left-hand side here, that there's a lot of nebulous material left over. This red material on the bottom here, that's part of the hydrogen gas cloud that originally formed all of these stars that are part of the open cluster. The beehive cluster doesn't have a lot of this material left over, and that's because as time goes by, the material is going to disperse literally into the Milky Way and into outer space. You have winds that come naturally from the young stars that have formed, as well as possible end-of-life stellar explosions nearby. And anytime you have these turbulent winds, you're going to blow away material and you're going to halt star formation. So within 10 to 100 million years, you have a gas cloud collapse. It's going to form a whole bunch of young stars. Maybe all of the cloud material forms stars. Maybe some of it is blown away, or maybe some of it is still there. But overall, you're going to form hundreds to thousands of stars in this small region of space. And you're going to end up with a star cluster, basically a region with many, many stars of different sizes and masses that are all fairly young compared to the globular clusters that we just talked about. So before we get into the science of things, I just wanted to show you a really nice collection of open clusters. Each one of the squares here, these are each an individual open cluster. So these are in all different regions of the sky, but we've collected them all together into one slide just to kind of give you a nice sense of what they might look like. So in each case, you can see stars of various colors. Generally, the colors will give you a sense of the sizes. Blue stars will be larger, more massive, and hotter. Red stars will generally be cooler and smaller, except for those that have evolved a little bit to be really bright red stars. But in general, you can see that each one is just a lovely collection of stars. Some of them have some of that red nebulous hydrogen material around them, and some of them don't, but each one is very unique, and each one is really, really beautiful to look at. All right, so now that we have talked about the basics of star clusters, let's talk a little bit about some of the science that we can do with them. One of the first things that we realized star clusters could help us out with is figuring out where we are in the Milky Way galaxy. If I just asked you that question, where are we in the Milky Way compared with the edge or the center of our galaxy, how could you answer that question? I've already told you previously kind of where we are, but if you didn't know, how could you figure it out? What are some techniques you could use? Well, 18th century astronomers thought they had the right idea. They used a very simple and very logical method they called the star counting method. The idea was this: if you go outside at night, you look up at the stars, and you see a roughly equal number of stars in every direction, then you are probably somewhere near the center of the galaxy because you're looking around and you can see equal number of stars in every direction. If you saw more stars in one spot in the sky and far fewer stars in the opposite side of the sky, then you probably were somewhere away from the center, and the center of the galaxy would be towards the concentration of stars. Makes sense, right? Very logical. If we had a general sense of what we think the galaxy would look like, then we would look for the biggest collections of stars, and that should tell us where we are in the Milky Way, or where the center of the galaxy is located. So when astronomers did this, they found that there was pretty much an equal number of stars in all directions. So they came to the natural conclusion that we must be at the galactic center. Now, this was long before they had any idea what a black hole could be, and they really didn't understand the true structure of a galaxy yet. So you have to forget about all of those possible ideas. But just basically going outside, and you can experiment with this. Go outside, look at the stars in any season, and you'll pretty much see an equal number of stars in all directions. So you might conclude that you are near the center of the galaxy. But in reality, as we've said previously, we are not anywhere near the center of the galaxy, which is a good thing, right? Because we don't want to fall in the black hole. We're actually halfway between the center and the edge. We're about here. We're on something called the Orion Spur, the inner edge of one of the spiral arms of the galaxy. So why didn't the star counting method work? Makes perfect sense, but why did the early astronomers get the wrong answer? Well, the main thing that they neglected to account for, which in their defense they really didn't know about yet, was the fact that our galaxy and the spiral arms of our galaxy are filled with gas and dust. And one of the things that gas and dust is really good at doing is blocking starlight. So it's kind of like, trying to look through smog, right? You can't see through thick, dense clouds. So those clouds are going to block your view of things that are far away. And that's exactly what was happening. If you go outside at night and you look towards the galactic center, you don't see any more stars in that direction than you do in the opposite direction of the sky. But that's not because there aren't more stars towards the center of the galaxy. It's because there's also more gas and dust blocking the light from the stars near the center of the galaxy. We call this extinction, where the gas and dust extincts or blocks the light. And early astronomers didn't know about this concept, so they made the mistake of thinking that we must be near the center of the galaxy. They didn't account for this extinction. But 20th century astronomers were a little bit smarter, and they figured out that if they look at these globular clusters, these clusters of stars, those clusters of stars seem to be concentrated in one direction in the sky. So take a look at the picture on the bottom right here. This is a map showing our Milky Way, the location of our sun, and the location of globular clusters both above and below the Milky Way. So here's the center of the galaxy. Here's where we are. Each one of the white dots is a globular cluster, and there are purple lines drawn straight down to the plane of the galaxy to try and give you a sense of where the globular cluster is located. All of these globulars are above the plane of the galaxy. All of these are below the plane of the galaxy. So imagine standing on the sun and looking in one direction and counting the number of globular clusters. If you look towards the right in this diagram, you're going to see a high concentration of globular clusters, either above or below the plane of the galaxy, it doesn't matter. They're all concentrated on this side of the picture. And if you look in the opposite direction, you're going to see few to no globular clusters at all. So these 20th century astronomers realized that globular clusters tended to be concentrated in one direction of the sky, and they seem to be most highly grouped together about 27,000 light years away. So that must be where the galactic center is. Instead of using just individual stars, they use the globular clusters to figure it out. Globular clusters are not as affected by extinction because they are above and below the plane of the galaxy. And most of the gas and dust sits within the spiral arms. It sits in the plane of the galaxy. So you have to worry about it when you're looking for individual stars, but if you're looking above and below the galactic plane, there isn't as much dust and gas to look through, so you're not going to have as much extinction. So counting the location and the distance to globular clusters, that is going to get you an accurate location of where you are in the Milky Way. And that's exactly how we know, even to today, where we are in the Milky Way. We look at the distance of globular clusters and kind of gauge where we are in relation to the center of the galaxy. Star clusters are really useful for helping us figure out where we are in the Milky Way, and they're also really helpful in determining the ages of stars in general, as well as the age of the Milky Way galaxy. So let's talk first about how we figure out how old a star is. It's actually very difficult to pick out a single random star and try and figure out how old it is. We can use some clues like its composition, its rotation rate, or its brightness, but we're not going to get a very precise value. We might be able to get an estimate but within a few billion years, but usually we want to be more precise than that. Now, our sun shown here is a little bit different because it's nearby, it's in our solar system, and we also have other objects in our solar system that can give us clues to the age of the sun. So we've determined that our sun is about 4.5 to 5 billion years old, and that's determined via a variety of methods. The first thing we can do is take a look at planet Earth. Ignore the sun completely and just take a look at our planet. We've got rocks. We can age date some of the oldest rocks on Earth, and we find them to be about 4.2 to 4.5 billion years old. We know, thanks to our theories of star and planet formation, that stars form first and planets form slightly after that. So we know that our sun must be slightly older than the age of Earth and the age of other asteroids or meteorites or rocks in our solar system. If we want to take some measurements specifically of the sun to try and get its age, we can do things like measure the ratio of helium to hydrogen that's inside of the sun. Figuring out that helium abundance is tricky, but we can utilize it to get an age because as a star goes through its life, it's going to constantly fuse hydrogen into helium. So the older it is, the more helium compared to the hydrogen it's going to have inside of the star. And we can figure that out using spectroscopy. We can also take a look at the luminosity or the brightness of the sun and compare that to models. We know that stars will change their brightness slightly as they age, so we can compare the sun's size and brightness to our models and see kind of where we think it is throughout its life cycle. And we can also compare it to rotation rate models. Our sun's rotation rate is going to change slowly in time because the mass in the interior is going to change, the size of the sun is going to change slightly, and that ultimately affects rotation rate, and rotation rate is fairly easy to measure. We can use Doppler shift techniques to figure out how quickly the sun is rotating. So ultimately, all of these pieces put together give us an age of 4.5 to 5 billion years. They all come to a consensus around that number, which is good. We can estimate the age of the sun. But for any other random star in the sky, we don't have all of that information. And in many cases, it's not possible to get a lot of this information. So we're left kind of wondering how to figure out the age of other stars. So the one thing we can do though is turn to star clusters. Doesn't necessarily help us with a single random star in the sky that we want to know, but it does allow us to get ages of any stars within the star cluster, as well as an approximate age for the entire Milky Way galaxy. If we can figure out the age specifically of those globular clusters, then we can get a sense for how old our galaxy is. So how do we do that? How do we use star clusters to determine ages? Well, the first thing we have to remember is that all stars in a star cluster likely formed from the same cloud, and that means that that cloud collapsed and all of the stars formed at roughly the same distance from us, and they all formed in approximately or at approximately the same time, within a few million years. Now, I know an error bar of a few million years sounds like a lot, but when you compare that to the average age of a star, which is, 1 to 10 billion years, then an error bar of a few million years is actually pretty small. It's almost analogous to thinking about your birth date, right? If you're going to live to be 100 years old, you really just need to know the year you were born, not necessarily the specific day or the specific minute that you were born. It doesn't really matter so much on the grand scheme of things. So with star clusters, we know that they all formed at the same distance from us, and they are all of the stars are about the same age. That is key. Here's one example. This is the globular cluster M3. It's about 34,000 light years away from our sun and our solar system, 90 light years in diameter, and it's about 11.4 billion years old. Okay, so that didn't answer our question though. How do we use star clusters to determine ages? Well, to do that, we need to understand how stars evolve and change with time, and we need to understand how the life cycle of a larger, more massive star is different from a lower mass star. So clusters, open and globular clusters both, when they first form, they contain stars of various masses. There are stars that can be up to as large as 150 times the mass of our sun, all the way down to something the size a tenth of the mass of our sun. So they really have a wide range, and all these stars are mixed together within the cluster. All of these stars are going to spend most of their life fusing hydrogen into helium. That's what stars do, that's how they generate energy, and that's why stars shine. So what we've noticed is stars that have a higher mass, so stars that are more massive, that are larger, they are going to, quote, burn through their, quote, fuel faster, meaning they are going to fuse the total amount of hydrogen that they have in their core at a faster rate than stars that are smaller because they are larger. They need to make more energy to hold up the star, so they're going to burn through their fuel faster. Ultimately, that means they're going to live a shorter lifetime, right? If you're burning through your fuel faster, you're going to live a shorter amount of time. If you take a look at the cartoon on the right-hand side, we have a couple of stars shown here, along with their sizes and their average lifetimes. We have a star called Spica, bright blue star that you can see in the sky. It's about 11 times the mass of our sun, and it has a lifetime of 10 to the 7 or 10 million years. If we go to a star like Sirius, smaller, only 2 times the mass of our sun, it has a lifetime of 10 to the 9 or 1 billion years. Our sun at 1 solar mass has a lifetime of 10 billion years. And stars that are smaller, like Proxima Centauri, one of the smallest stars we can possibly get, it's about 0.12 times the mass of our sun, and that could have a lifetime as long as 1 trillion years time. So you can see the general trend here. The more massive the star, the shorter the lifetime. Now, there's a simple expression you could think of for lifetime here. Lifetime is equal to the total amount of fuel that you have divided by the rate of fuel use, right? You have to take how much fuel, how much hydrogen do you have, how quickly are you going to burn through it, and taking the total divided by the rate of usage, you end up with your lifetime. Now, the best way to think about this, because we're talking about fuel here, is with vehicles. And you can see that I've put a couple cartoon cars over by our stars. So if this whole star thing doesn't make sense to you, I want you to think of it in terms of cars, of trucks, SUVs, and smaller fuel-efficient cars. And we're going to use this analogy throughout the rest of the presentation so that you can understand and follow along with what's going on. Our more massive star like Spica is exactly like a truck. Giant gas tank can hold a lot of fuel, but it has really poor gas mileage. So you're going to have your truck, it's going to burn through its fuel faster, and it's not going to be able to go as far as a fuel efficient car, even though it has a bigger gas tank, because it gets lower gas mileage. Stars like the Sun or Proxima Centauri, they are going to be your small fuel efficient car. They have smaller gas tanks, but they're much more efficient at burning their fuel, so the car can go further even with a smaller gas tank. That's the analogy we want to have. So keep that in the back of your mind. Big stars are trucks, little stars are fuel-efficient cars. Okay, so now that you understand how the size and mass of a star is linked with its overall lifetime, we can introduce you to the most important graph in astronomy, the HR diagram, or the Hertzsprung-Russell diagram. And it's with this graph that we are going to be able to determine the age of star clusters. So what is on this very special graph? Well, basically, it's a way for astronomers to plot properties of stars. We can plot information like a star's mass, size, temperature, power. All of that information is buried in this one graph. So before we actually look at the individual stars, I want you to just focus on the axes of the graph. First, if we look at the y-axis here, this is luminosity. How much power is the individual star emitting? And the numbers here are in solar luminosities. So anything with the number 1, so anything along this imaginary line here, that would be same amount of power as the sun. Anything up here would be more powerful, emitting more light than the sun. And anything down here would be less powerful than the sun, emitting less light than the sun. The x-axis is a little bit tricky because it's backwards from what we normally do on a graph. The x-axis is the surface temperature of the star, where we have hotter stars on the left and colder stars on the right. The colors are also analogous. In general, we have bigger, hotter stars as blue, smaller, colder stars as red. So the colors are corresponding to the temperatures. You also see that there's some letters here, O, B, A, F, G, K, and M. Those are spectral types, and we're not going to get into the details of spectral types in this lesson, but just know that these letters correspond to the order of stars from hottest to coldest. So O is the hottest, B is the next coolest, A is the next coolest, all the way down to M, which are the smallest and coldest spectral type stars on this diagram here. So when we plot stars on this graph, we find that most of them lie along this approximately straight diagonal line here, and we call it the main sequence. This is where stars are fusing hydrogen into helium, and we'll talk more about that in a moment, but most stars will lie along this line. As stars evolve, they become giants. They start to puff out. And as they age, they'll either become regular giants or they'll become supergiants, depending on whether or not they started out as a small star or a big star in the beginning. This is the information that we get on these diagrams here. And if we want to go back to our car analogy, we can do that. In the upper left here, we have our really large, really hot stars. This is going to be where the trucks are. These are the high mass stars that have a very short lifetime. And in the bottom right, we have our low mass stars that have a much longer lifetime. So blue truck in the upper left, red car on the bottom right. Okay, so our small fuel efficient cars on the bottom, high mass stars, our trucks with low fuel efficiency are in the upper left there. So as we said, stars spend most of their lifetime on the main sequence. They're fusing hydrogen into helium, they're making energy, they're shining very brightly. And when the stars start to age, they start to die off, what they will do is they will move off the main sequence into the giant or supergiant range on this diagram. So if I took a snapshot of a really young star cluster, all the stars would be on the main sequence because they're all actively fusing hydrogen into helium. But as time goes by, you will see that the stars will eventually move into the giant or supergiant range and they'll start populating the upper right corner of this diagram. You can think about this as the point where the star, or the car runs out of gas, right? So remember, our trucks are up here, our cars are down here, and as the cars and trucks run out of fuel, they pull off to the side of the road, okay? They shift to the right in this diagram. So our trucks are going to move over into the supergiant range as they run out of fuel, and our cars are going to move into the giant range when they run out of fuel. So the cars are normally driving down the road, driving down the main sequence until they start to run out of fuel and they pull over to the side into the giants and supergiant range. All right, so now we need to talk about what's going to happen to these stars and understand how looking at an HR diagram actually tells us age. We're going to go through this candle analogy first with stars and then again with the vehicles so that we are all on the same page. In a star cluster, remember, all the stars are the same age. Time 0 is the same for all the stars. We'll pretend that we snap our fingers and all of the stars are born at exactly the same instance. As time elapses, what happens is the more massive stars evolve first. Then the lower mass stars will progressively evolve as time goes by. A good way to think about this is to use a candle. The candle represents all the stars that are currently on the main sequence. So here's our candle, and we've listed them in order from hottest to coldest. Remember those letters O, B, A, F, G, K, and M, hot stars at the top, cold stars at the bottom. If my candle on the left is the beginning, time equals 0, I light the candle and I let it sit. What's going to happen to the wax of the candle? Well, as time goes by, you can see that the wax is disappearing, right? The candle is burning down, and as time goes by, the candle gets smaller. As time progresses, the stars that are left on the candle are less and less massive. So originally I have all the stars, the big ones and the small ones. As the candle burns, I start to lose the biggest stars. And as time goes by, more and more large stars disappear. They move over into the giant or supergiant range. And after a very long time, the only thing that's left on the candle are the lowest mass stars, the K and the M type stars. So as time goes by, the only stars that are going to be left on the main sequence are the stars that are lower mass, that take a lot longer to evolve, the ones that have a longer lifetime. So to summarize, what this means is the older the star cluster, the less stars we will see on the main sequence overall, and the only stars that will be visible on the main sequence are the lower mass stars. The higher mass stars, they will have evolved off. So if that's confusing you a little bit, let's go back to our car analogy. All cars start with a full tank of gas, right? Time 0, all my cars are lined up. They have a full tank of gas, however big their gas tank is. As time goes by, if we start all the cars and time goes by, they're all driving along the main sequence, they're driving down the road. Eventually, the cars are going to start to run out of gas. The trucks, the big ones, they are going to run out of gas first and they're going to pull over. Next are going to be maybe my SUVs. So I've introduced a new car here, an SUV in the middle. An SUV will run out of gas second, so that will pull over. And the car is going to have the highest fuel efficiency. That's going to take the longest time before it has to pull over because it's not going to run out of fuel until a much greater time has passed. So the longer we let the vehicles run, the less vehicles will still have gas left, and the only cars that have gas left are going to be the small cars. So looking at our candle here, remember our trucks were at the top, our massive stars. As time goes by, eventually all the trucks will have pulled over. The only cars on the road are going to be the SUV and the cars. And as more time elapses, the SUVs will pull over and only the cars will be driving until a point where all of the cars will run out of gas and there won't be any of them driving down the main sequence. There won't be any of them driving down the road anymore. So by looking at the types of vehicles that are still running on the main sequence, that's how we can tell the age, right? If we see trucks and SUVs and cars, then we know we're early on. The cars haven't been driving for very long. The analogy is the star cluster is young. If we look at the star cluster and we only see lower mass stars, we only see cars driving down the road, no trucks or no SUVs, we know that the star cluster is older. The cars have been driving for a longer amount of time. So we have to link this back to the HR diagram. How do we use real data, real information about the stars to determine the age of the cluster? Well, first we have to make an HR diagram of a cluster, and a great example is shown here. This is an HR diagram of the globular cluster M55. Every single dot represents the property of one individual star inside of this cluster that has thousands of stars, right? There's thousands of dots on the diagram, so there's thousands of stars in the cluster. The diagram is exactly what we've seen already. We have high temperature stars on the left, cooler stars on the right. We have very powerful stars along the top and not so powerful stars on the bottom. You can ignore the other additional numbers and axes that are labeled. We're not going to focus on them today. Some key things to notice on this diagram here. First, we need to find the main sequence, right? Where are the stars driving down the road? Well, the main sequence is this red line here. Any star that falls along this red line or close to it, those are stars that are actively fusing hydrogen into helium. Those are the stars that are still on the main sequence. You can see that there's a lot of red and yellow dots on the main sequence, a lot of lower mass stars, not a lot of higher mass stars on the main sequence. There's a lot of dots in different regions of the diagram. There's blue dots up here. These are supergiants. These are the trucks that have pulled over to the side of the road because they've run out of fuel. And these are the SUVs and some of the smaller cars that have pulled over to the side of the road because they have run out of fuel too. These are stars that have become giant stars. So the important thing to notice about this HR diagram is the fact that there's a big chunk of stars missing from the main sequence here. And at this point, this is where we start to see stars still on the main sequence. But after that, more massive than that, the stars are generally missing, except for a few blue stragglers here. But we can ignore those for now and just notice most of the stars are missing here. Lots of stars are still on the main sequence on the bottom. So that key point where the graph kind of takes a right-hand turn, that is called the main sequence turnoff. That is the point where stars are no longer on the main sequence. They have pulled over. They are turning into giants or supergiants. The lifetime of stars at the main sequence turnoff point tells us the age of the star cluster. This is exactly how we're going to figure out how old the stars are. So by looking at this position, we can figure out, okay, a star at this position, whatever size or mass it is, we know how long that star should be on the main sequence. So any stars right here, that tells us they're just evolving off the main sequence, so the cluster must be that age. Because stars are missing up here, we know that the stars that live a shorter lifetime have already died off, so the cluster is not very young. The cluster must be a little bit older because it only has stars down here. It only has red cars left. That's the way to think about it. So let's summarize and finally answer the question. How old is globular cluster M55? Well, we said the older the star cluster, the less stars we will see on the main sequence. So looking at the main sequence here, stars that are at this position, stars that are at the main sequence turnoff, they survive for about 12.7 billion years before they start to evolve to become giants. So stars that live less than 12.7 billion years old, those would be the stars up here, they have evolved. They have become giants or supergiants. Stars that live longer lifetimes than 12.7 billion years, that's all the red and yellow stars down here. They're still on the main sequence. They're still living out their strong life. This turning point where the stars start to evolve, that age at that location is about 12.7 billion years. So that tells us how old M55 is. And just one more time to bring out the car analogy here. Again, we've got our trucks. They're up at the top, our cars at the bottom, our SUVs in the middle. The cars and the SUVs in this, or excuse me, the trucks and the SUVs in this case have run out of gas. They've pulled over, right? But there are still cars driving down the road. These cars live for a very, very long time. And by figuring out exactly how long a car at that specific position should be able to drive down the road, that tells you exactly how old the star cluster is. Tells you exactly how long all the cars have been driving down the road. So by using the main sequence turnoff point in an HR diagram, that is how we figure out how old a star cluster is. And every star in the star cluster is that age. They will be at different points in their evolutionary cycle because some stars evolve faster and some stars evolve slower, but they all are the same overall age. So I'm going to do one more example here. This is the Pleiades. Remember, you can see the Pleiades in the constellation of Taurus in the wintertime sky. We can draw an HR diagram for the Pleiades, and that's what we have on the right-hand side. So again, brightness of the stars, or power really, luminosity, temperature, high temperature on the left, cold temperature on the right, and all of these triangles represent individual stars in the Pleiades. The main sequence is that colorful diagonal line here. Notice that most of the stars fall on the main sequence. We have low mass stars and high mass stars on the main sequence. And right about here, where we've labeled the main sequence turnoff, there's a handful of stars that have turned off to the right, a handful of trucks that have pulled over, if you will. So by looking at the stars right here that have just moved off the main sequence, that have just reached the point of evolving, we can figure out how old the Pleiades is. Now I'm going to put some numbers up here to show you what the ages are at the different locations of the turnoff points. So here, if there were stars in the main sequence up here, these stars evolve off the main sequence in 10 million years, 10 to the 7 years. Stars here evolve at 10 to the 8 years, so 100 million years, a billion years, 10 billion years, and 100 billion years. Where is the main sequence turnoff? Well, the stars right about here are the ones that are evolving off. Those stars survive on the main sequence for about 10 to the 8 years. They survive for about 100 million years. So we know that the Pleiades must be 100 million years old. If it were younger than that, we would see stars all the way up to the top. If it were older than that, then none of these stars would be there. They'd all be hanging out in the upper right-hand corner of the diagram. So by looking at this main sequence turn-off point right about here, we can figure out that the Pleiades is a really young star cluster. And that makes sense, remember? Open clusters are younger than globular clusters. We just saw M55 was over 12 billion years old. The Pleiades only 100 million years old. So how can we use this technique to figure out the age of the Milky Way? Well, remember that globular clusters formed when the Milky Way was forming. So all we have to do is measure the age of all the globular clusters, or as many as we can see at least, And that will give us a rough idea for how old the Milky Way is overall. When we do that, we find that the oldest globular clusters in the Milky Way are around 10 to 12 billion years old. And we do that by looking at the main sequence turnoff point. So here's globular cluster M4, a globular cluster in the Milky Way. Here's the HR diagram. All the X's are representing stars that are part of the cluster. Here's the main sequence. Note the right-hand turn, that's the main sequence turnoff. It's right near where the sun would be located in this diagram, and the sun lives for about 10 billion years total. So in M4, you can see the main sequence turnoff point is right around 10 billion years. So this cluster must be about 10 billion years old. And that's what we find for most globular clusters in the Milky Way. They're all about 10 to 12 billion years old. So our Milky Way galaxy must be 10 to 12 billion years old as well. That's how we can estimate the age of our own galaxy. Okay, so I know that was kind of scientifically intense, but hopefully now you have a better understanding of how we figure out the ages of stars and star clusters and how we figured out the age of our own Milky Way galaxy. We're going to finish up on a much lighter note, just showing you a couple of globular clusters that you can go out and look for in the night sky tonight. If you go out in the late spring or early summer, you can look for the Beehive cluster in the constellation of Cancer the Crab. Now, Cancer the Crab is a pretty faint constellation, so you can look for some other brighter stars nearby. Look for the backwards question mark of Leo with bright star Regulus on the bottom. And also look for Castor and Pollux in Gemini if Gemini is still visible. And these stars will guide you down about halfway in between those two constellations. You'll see a small fuzzy patch. Take a pair of binoculars or a small telescope and point it at this cluster, and you'll see a whole bunch of individual stars that kind of look like a swarm of bees. That's where the name the Beehive cluster came from. If you're out in the summertime, you can look south for the constellation of Hercules. Look for what's called the keystone or the trapezoid here. And halfway in between these two bright stars, Eta Hercules and Zeta Hercules, there'll be a little fuzzy patch, little fuzzy cloud, and that'll be the Great Cluster of Hercules, or M13. It's another great one to point a pair of binoculars at or a small telescope if you have it, and you can really clearly see those individual stars. So I encourage you to go outside, look for these star clusters, and just look for any beautiful constellations or fuzzy patches that you see. There are a lot of star clusters out there, and if you happen to live somewhere that has pretty dark skies, you'll be able to see a lot more of these clusters and objects in the sky. So that's it for our astronomy lesson today. I hope you enjoyed it. Next month, our lesson will be Wonders of the Summer Night Sky. So we'll get into detail about how you can find different constellations, how you can find the summer triangle, and even how you can spot the Milky Way and look towards the direction of the center of the galaxy. So hopefully you can join us for next month's lesson. Until then, stay safe and healthy, and I'll see you again soon.